In question 1, part A, because the gravitational field A can be considered to be uniform over the short distance 10 meters above the surface, we can just use G delta H to calculate the value of the potential difference. So in this case, that is just 19 times the 10 meters, so we end up with 190 joules per kilogram. In part B, the minimum amount of energy required to lift a 9 kilogram rock, we'll just use mg delta h, so it's 9 kilograms times 190 joules per kilogram, and that gives us an answer of 1710 joules. In part 3, which is state whether the minimum amount of energy found would be different if it were lifted 10 meters from a point near the top of the highest mountain on planet X. If you're near the top of the highest mountain, your distance from the centre is obviously much greater. Because the value of G is proportional to 1 over r squared, G will be smaller at the top of the highest mountain, so therefore the energy required to lift the rock would also be smaller. So how we'd argue this is we would say, so G is smaller, therefore mg delta h is less. The energy required is less. For part B, the key information here is that the planet has the same mass but twice the diameter. So again, we use the formula gravitational field strength. We'll do it for planet Y is G, our mass is the same, over, now if it's got twice the diameter, it must also have twice the radius, which gives us Gm over 4 r squared. So our gravitational field strength will be a quarter of the gravitational field strength on X, which was 19. So we'll do 19 divided by 4, which gives us a gravitational field strength of 4.75 newtons per kilogram. First of all, we have to find the potential at a distance 2r from the centre of the Earth. This is minus 31 megajoules per kilogram. It then asks us to find out the increase in potential energy of a 1200 kilogram satellite which moved from the surface of the Earth into an orbit of radius 3r, which is in the centre there. This is taking it from minus 62.5 megajoules to a potential of minus 21 megajoules. So that is an increase in potential of 41.5 megajoules per kilogram. The final part of question 2 asks us to use the graph to calculate the gravitational field strength at a distance of 2r from the centre of the Earth. In order to do this, we need to find out the potential gradient of the graph here, and we need to draw a tangent to our line. Now, with the device that I'm using, it might not be that straightforward to do. You do need to use a ruler, and you do need to do this very, very carefully, just touching the line. So let me try that without moving it, and it just about worked, I think. So looking at this, I've got an intercept at minus 62, so my my delta y is 62 times 10 to the 6, and my delta x, my intercept here appears to be at 3.9 r, which is 6,400 kilometers, so that's 10 to the 3 meters. Okay, and so the calculation for this will appear on the next slide. This was minus 31 megajoules per kilogram, and the increase in potential energy is worked out by multiplying the mass times the increase in potential, which was 41.5 times 10 to the 6 joules per kilogram, and that gives us an increase in potential energy of 5 times 10 to the 10 joules. An equation which relates gravitational field strength and gravitational potential is that G is equal to minus the potential gradient. And this is what we calculated on the last slide. the gradient of the graph was going to be worked out by 62 times 10 to the 6, which was my change in y, divided by my change in x, which was 3.9 squares, times 6,400 kilometers per square, which gives us 62 times 10 to the 6 divided by 2.496 times 10 to the 7. And this comes out as 2.5, and that is newtons per kilogram. We need to use G is proportional to 1 over r squared. If we double r, it leads to G becoming a quarter of its initial value, because doubling r becomes 2r. 2r all squared becomes 4r squared. So we can say if at the surface it's 10 newtons per kilogram, at 2r it's going to be 10 over 4, which is 2.5 newtons per kilogram, which we can state is the same as we found in our previous answer. For question 3, it's worth us learning a method, because this comes up quite often. Whenever a question mentions radius and density in a multiple choice, this could be quite time consuming to work through all the various factors. But if we remember that mass is equal to density times volume, and that planets are spherical, and the volume of a sphere is 4/3 pi r cubed, we end up with mass being proportional to density times r cubed. G, we know, is proportional to the mass of the planet divided by its radius squared. We've just said mass is also proportional to r cubed, so we can say now that G is proportional to rho density times radius cubed divided by radius squared. So these things cancel. So in fact G is just proportional to density times radius. So in planet Q we have double the radius and half the density. If we double one thing and half the other, because gravitational field strength is just proportional to density times radius, that has no effect at all. So it will be exactly the same, which is B, 13.4 newtons per kilogram.